So, good morning everyone. Here I am going to record a lecture on intrinsic and extrinsic semiconductors. In electronic devices, we have already discussed about the basic concepts of semiconductors. So, this is in continuation with the last lecture, lecture 4. This is lecture number 5, which comprises of intrinsic and extrinsic semiconductors. So, we have already discussed about the elemental semiconductors, the compound semiconductors and their various materials. So, we have already discussed that in the elemental semiconductors, we have silicon and germanium. In the compound semiconductors, we have third and fifth group elements, which are gallium arsenide, indium phosphide and so on. So, here the classification is based on the impurity content. So, the semiconductors are divided into two types. The first one is the intrinsic and the second one is the extrinsic semiconductors. So, extrinsic has also two types, that is P type and N type semiconductors. So, what we are going to see here, that how the impurities will contribute to the conductivity of the semiconductors. So, as we have discussed in the previous lectures, that the semiconductors conductivity can be improved to a variable extent. We can use it in various applications. So, in the intrinsic semiconductor, which is called as a pure form of semiconductor. So, intrinsic is called pure form of semiconductor. On the other hand, extrinsic semiconductors are those semiconductors in which we provide some doping. We provide some doping of P type doping or N type doping. We have some third group elements doping or some fifth group elements doping. So, normally the semiconductors are for the fourth group elements. But if we provide some third group doping and fifth group doping, then it becomes extrinsic type. So, we are providing externally doping or adding impurities into the semiconductor. So, if we provide external impurities to the semiconductor, it becomes extrinsic type. So, here we are going to see what is the difference between intrinsic and extrinsic semiconductor. So, you can see the first one, the intrinsic semiconductors are pure group 4 elements. So, as I have discussed that pure group 4 elements are intrinsic, which are called as pure type of semiconductors. On the other hand, the third and the fifth group elements are introduced in the group 4 elements. So, we have to introduce third group or fifth group elements so that there will be some impurities added into the intrinsic type semiconductors and we can improve the conductivity of the semiconductor. So, in the case of the intrinsic semiconductor, the conductivity is only slight. Only there is a slight conductivity in the case of the intrinsic type of semiconductor because it is a pure type of semiconductor. On the other hand, extrinsic semiconductors conductivity is greatly increased. We can easily increase the conductivity of the pure type of semiconductor by adding impurities of third group or fifth group elements. Similarly, conductivity increases. What is the effect of temperature in the conductivity of the intrinsic and extrinsic? So, conductivity increases with rise in temperature in the case of intrinsic semiconductor. On the other hand, conductivity depends upon the type of the amount of the impurity added onto the semiconductors on the basis of particular doping, like a third group element doping is there or a fifth group element doping is there. According to that, conductivity vary. Fourth point is the number of holes is always equal to the number of electrons. So, here N is equivalent to P, number of electrons is equivalent to P in the case of the intrinsic type semiconductor. So, normally N is equivalent to P is equivalent to Ni square when we solve for different relationship for the carrier concentration of electrons and holes in intrinsic type semiconductor. So, there we represent N naught and P naught is equivalent to Ni square. In the case of the extrinsic type semiconductor, in N type, if we are talking about extrinsic type, so in N type semiconductors, we have the number of electrons to be more as compared to the number of holes. So, the number of electrons is greater than number of holes. So, N is greater than P in the case of N type of semiconductors. On the other hand, if we talk about the P type of semiconductors, so in that case, P type of semiconductors, number of holes is greater than number of electrons. So, there the number of holes are much more greater than the number of electrons because we are doping third group element like boron into the fourth group element and we have a donor type acceptor type of impurity to be added there has to be added there. So in that case, the number of holes is greater than number of electrons. On the other hand, if we add gallium or arsenic type impurities into the fourth group elements, then in that case we have number of electrons much more greater than number of holes. So coming to the energy band diagram in intrinsic and extrinsic semiconductors. So we can see easily that intrinsic semiconductors are pure type of semiconductors, and we have in the diagram also that there are silicon elements or atoms are there, and it has a covalent bonds with other silicon atoms, and there are no any impurities added into the intrinsic type of semiconductor. On the other hand, extrinsic n-type semiconductor, donor semiconductor, they have extra electron. So if there is extrinsic n type of semiconductor, it have extra electron, but if it has a extrinsic p type semiconductor, acceptor type semiconductor, it is also called acceptor type semiconductor, and they have a vacancy created. So you can see from the diagram, in the extrinsic n type semiconductors we have arsenic type of impurities, so which is basically a fifth group element added to the intrinsic semiconductor. Similarly, in the extrinsic p type semiconductor we have gallium type of impurities. So arsenic and gallium, arsenic is the third group element and the gallium is the fifth group element. So we have added the third group and the fifth group element into the silicon lattice structure. So from these diagram, band gap diagrams, you can see that there is a valence band, there is a conduction band. In the intrinsic type of semiconductor, the Fermi level, because the Fermi level is what? The Fermi level defines the number of electrons or holes at a particular state. So the Fermi level is in between, because the number of electrons and holes are equal in the case of intrinsic semiconductor, n is equivalent to p is equivalent to ni. That's why the Fermi level is in between the EC and EV. So here in the intrinsic type, the Fermi level EF is equivalent to EC plus EV by 2. It is midway between EC and EV. So the Fermi level is in midway between EC and EV in the case of intrinsic. But on the other hand, if we see about extrinsic n type of semiconductor, because there is a doping of fifth group elements, so extra electrons are there. So it has a donor type of impurity. So there is a donor state. So the donor state and the Fermi level shift upwards. So from the midway, the Fermi level shift upwards will just below the conduction band, and there is a donor state, so that the electrons can be donated from this state to the conduction band. So you can say that the number of electrons in the conduction bands keeps on increasing as we have n type of doping there. Similarly, on the other hand, we can see that in the case of the p type extrinsic semiconductor, the Fermi level is just below the midway. So the Fermi level is just below the midway and it is above the valence band, and it has a acceptor type of impurity. So if it has a acceptor type of impurity, it will accept atoms or electrons from the valence band and create a vacancy in the valence band. Here it is a vacancy. So here we have n is equivalent to p is equivalent to ni for the case of the intrinsic semiconductor, because number of electrons and holes are equal. For n type of doping or n type of extrinsic semiconductor or the fifth group elements doping, we have n is very much greater than p. For the whole third group elements like arsenic, we have n is very much less than p. So these are three states or the three conditions of the energy band gap diagram for intrinsic and extrinsic type semiconductors. So classification of semiconductors on the basis of the charge type. How we can classify the semiconductor on the basis of the charge type? It can be of n type, it can be of p type. So as usual, as I have told you, that n type is a donor type of impurity because it donates electrons into the particular conduction band or a particular band. A p type is the acceptor type of impurity. It will accept the electrons from the band and create the vacancy there. Impurity atom is pentavalent type. In the n type, it is pentavalent because the fifth group elements we are taking care of. So the outermost shell has 5 atoms. So the impurity atoms is trivalent here. So here the impurity atom is trivalent. Donor level lies close to the bottom of the conduction band. We have seen that the In the N-type extrinsic semiconductor, we have the Fermi level shifted towards the conduction band and it's just below the conduction band. In the case of the P-type, we have acceptor level lies close to the top of the valence band. It is just above the valence band. So, it has a acceptor type of impurity. So, here is a diagram for doping antimony in the silicon lattice and a doping of boron in a silicon lattice. So, if we dope antimony in a N type of semiconductor or a silicon structure, so it becomes N type of extrinsic semiconductor, and donor impurity contributes basically free electrons. So, there will be some free electrons. On the other hand, in the P type of semiconductors, we have acceptor impurities which creates a hole. Obviously, it will create a particular hole or a vacancy. So, these are the diagrams for energy band gap for N and P type semiconductors. So, N type semiconductors are donor type, we have discussed. Fermi level is near the conduction band, we have already discussed. P type semiconductors are acceptor type and Fermi level is near the valence band. So, we have arsenic type or boron type doping. In the first case, we have arsenic, which is a pentavalent impurity atom. In the second case, we have boron, which is trivalent impurity atom. So, you can see that from the diagram that there is a valence band and conduction band energy on the y-axis. The donor level is just below the conduction band in the case of the N type of semiconductor because the Fermi level shifts upward towards the conduction band. And in the second case, in the figure number B, we have energy band diagram like the valence band and the conduction band, and there will be a Fermi level shift downwards towards the valence band, just above the valence band. So, here it has donor type of impurity, it has donor impurity and it contributes free electron, donor impurities or free electrons. Here it has acceptor impurity and it creates holes or vacancies. So, basically this diagram, the purpose of this diagram, how the donor atoms or how the impurities will useful for the change or in the variation of the conductivity of the semiconductor. So, by this diagram we can easily see that the donor impurity add extra electron and the acceptor type of impurity add extra vacancies or the holes in the silicon lattice. So, this is a diagram for N-doped silicon, extra electron is there, you can see easily visualize here for the pentavalent type of impurities. For the P type of doped silicon which has a missing electron or a creation of the hole. So, here we have trivalent type impurity and here we have pentavalent. So, next we have the effective mass. So, effective mass is defined as the actual mass of the charged particle multiplied by a mass of the free electron. So, basically effective mass is used in terms of the when we have the atom has two forces, the internal forces and the external forces. So, we use mass into acceleration equation and there the mass is known as effective mass. If we use that F is total F internal plus F external, and there we use F is equivalent to MA, which is basically here M star A, where M star is the effective mass. We have already discussed in the last lecture. So, there are two equations for effective mass in the valence band and the effective mass in the conduction band in terms of the wave number. So, here we define in the valence band the mass of the free electron and the rate of the change of energy, the mass of the free electron and the rate of the change of energy with wave number is greater than 0. So, in the case of the valence band, we have d by square E or d square E upon d k square is greater than 0. Here effective mass is greater than 0. In the case of the conduction band, it is d square E upon d k square is less than 0 and it is basically effective mass is less than 0. So, M star is greater than 0 for the valence band and M star is less than 0 for the conduction band. So, here there is a table showing germanium, silicon and gallium arsenide. We know already that the effective mass for Mn that Mn star is for electrons and the effective mass for Mp star is for the holes. So germanium has effective mass around 0.55 m naught, silicon is 1.1 m naught, gallium arsenide is 0.067 m naught. Similarly, for the holes it is 0.37 m naught for germanium, then for silicon is 0.56 m naught, and for gallium arsenide it is around 0.48 m naught. So the effective mass is varied from germanium to gallium arsenide, as we have the elemental semiconductors, and for the compound semiconductors it is different. So we have the relationship in terms of energy versus k, or the wave number, day by square E upon day by k square is greater than 0 for the valence band, and for the conduction band it is day by square E upon day by k square is less than 0. Now we will going into the details of this, that how the Fermi level is important in the semiconductors physics. So the level at which the probability of finding an electron becomes maximum is called as Fermi level. So we define Fermi level in various ways, but the probability of having an electron at a particular state is maximum is called as Fermi level. So for a semiconductor, the probability of finding electrons becomes 50%. This means that the number of electrons and holes, or you can say the state is filled with half of the electrons and half of the holes. So it has a probability of finding electrons becomes 50%. So there are some terminology. First one is EF, which is Fermi level. EV is the energy of the valence band. K is Boltzmann constant. T is absolute temperature in Kelvin, or Ln is natural log, which is to the base E. Nv by Nd is the concentration of charge carriers in donor level, or Na is the concentration of charge carrier in acceptor level. So we have the relationship for the Fermi level, that is EF is equivalent to EV plus KT Ln Nv by Na, or Nd by Na, you can say, you can write it EF is equivalent to EV plus KT Ln Nd by Na. Nd is the donor type of impurity or the concentration of the charge carrier, or Na is the acceptor carrier charge concentration. So the Fermi level is defined by this way. So we have the Fermi level in between when Nd is equivalent to Na, means the number of donor and the number of acceptors are same. So in that case, the Fermi level is in between the, or Nd is greater than Na, it is in the conduction band, or Nd is less than Na, it is in the valence band. So this diagram shows the in between Fermi level between the EC and EV. So we have EF is in between EC and EV. We have EF is equivalent to EC plus EV by 2. So it is the case for the intrinsic, obviously. It is the case for the intrinsic type of semiconductor, which is pure form of semiconductors. So the Fermi level lies just in between the EC and EV. So EF is equivalent to EV plus KT Ln Nd by Na. So how the position of the Fermi level changes, as we have already discussed, firstly the conduction, in between the conduction and the valence band, the Fermi level is in between. For the N type, it shifted towards the conduction band. For the P type, it shifted towards the valence band. So existence, what is the existence of the Fermi level? No Fermi level exists in an insulator. This is a major point, that there will be no Fermi level exist in the insulator. In the case of the conductors or metals, it is hidden. In intrinsic semiconductors, the Fermi level lies exactly in between the energy gap. We have already discussed that the Fermi level is in between the EC and EV. In conductors, the Fermi level lies inside the overlap region. That's why it is something hidden between the conduction band and the valence band. So here there is a diagram showing the insulator, the semiconductors and the conductors. In the insulator, because there is a very large gap between valence and conduction band, there will be no existence of the Fermi level, because the occupancy of the electrons and holes are not there. In the case of the semiconductor, is in between the EC and EV. In the case of the conductor, as the valence and the conduction band is overlapped, so it is something hidden in between the conduction and the valence band. So this is the case for the metals. So now coming to the concentration of the charge carriers. So there are some equations related with the concentration of the charge carriers. The first equation is for the electron. So N0 is equivalent to Ni is equivalent to Nc exponential minus Ec minus Ef by Kt. So here there are two relationships. N0 is equivalent to Nc, N0 is equivalent to Nc exponential minus EC minus EF by KT. So this relationship, this is first relationship NC, and the second relationship is for the holes, that is P naught is equivalent to NV or PI NV exponential minus EF minus EV by KT. So these two relationships gives you the concentration of the electrons in the Fermi level or the in the particular state, and the concentration of holes in the particular state. So the intrinsic concentration is defined as Ni, and the number of concentrations or the total concentration of electrons is defined by N naught. So N naught is equivalent to Ni exponential, Ni is equivalent to Nc exponential minus Ec minus Ef by Kt. And this comes from the Fermi direct distribution function. We will discuss it later on. Fermi distribution function. So we will discuss it later on. So, and similarly for P naught, it is Pi, the intrinsic holes, is equivalent to Nv, that is the concentration of the holes in the particular state, exponential minus Ef minus EV by KT, where K is the Boltzmann constant and T is the absolute temperature. So the Fermi direct distribution, which is a very important distribution, it's basically tells you the density of states, or tells you how many states exist at a given energy. So how many states are there at a given energy, and thus this Fermi level is basically the function of the energy. So it is defined as the function of the energy, or F of E, and it is specify how many of the existing states at the energy will be filled with electrons. So we have to see how many states are filled with electrons. So the function Fe specify under equilibrium condition, and that the probability that an available state at an energy E will be occupied by an electron. So it is a probability distribution function basically, and Fe is defined as 1 upon 1 plus E minus Ef by Kt, where E is your energy, total energy, Ef is your Fermi level or the Fermi level energy, you can say, K is the Boltzmann constant and T is the temperature. So for the conduction band and for the valence band, the equation will change. For the conduction band, it has F of Ce notation, and for the valence band it is F of E notation. So for the conduction band it is Ec minus Ef, because Ec is above the Ef, so Ec minus Ef, and for the valence band it is Ef minus Ev, so it is Ef minus Ev by Kt. So these are the two relationships for the Fermi level, for the conduction band and the valence band. So normally we have a photon arrangements in some statistic, or in some statistic we use Boltzmann approximation. So there are two approximation, one is Boltzmann and second is the Fermi direct distribution. So these approximations are used for the probability of getting the overall number of electrons in a particular state. So Boltzmann is also a statistic which is used for photons, for getting how the photons in the population inversion state getting into the conduction band or in the lower energy level. So we have, suppose we have two energy levels, E1 and E2. So electrons are moving from here to here, and it is then come from by stimulated emission or by spontaneous emission and release some energy. So the release of the energy is defined in terms of Boltzmann statistic in the case of the photon. On the other hand, if we talk about semiconductor devices, we have Fermi direct distribution, and it is defined as F of E is equivalent to 1 upon 1 plus E minus Ef by Kt. So there is change of Fermi level with temperature. So for temperature is equivalent to 0, their Fermi level is at Ef. For temperature greater than 0, the Fermi level is greater than Ef, and for temperature less than 0, the Fermi level is less than Ef. So we have three cases. By graphically, I have shown you that the Fermi level for T is equivalent to 0, it is at 1. For Fermi level, for T greater than 0, the Fermi level shifted slightly towards the H, so towards the conduction band. Then again, if you or increase your temperature, then it again shifted towards conduction band, or if you reduce the temperature, it will just be like this. So for T greater than 0, it comes to the conduction band, towards the conduction band, and for less than 0, it towards the valence band. So this is the change of the Fermi level with with temperature. So now the last topic of today's, that is the carrier transport equation. So we have two type of carrier transport, that is the drift and the diffusion. So the drift is defined as the movement of the charge carriers due to the electric field. So if there is a movement of the charge carrier due to the electric field, it is called as drift current. And if it is defined as the movement of charge carriers from high concentration region to low concentration region, so it is called as diffusion. So with the diagram, I am going to show you that how the carrier transport equations are there. So carrier transports is as drift, and the diffusion, the movement of carrier due to the electric field. So we have a particular type of semiconductor. We have applied the voltage, the positive terminal and the negative terminal. So the electric field flows from positive to negative side, and the electron will flows opposite to the electric field direction, that is from negative to positive side. Similarly, on the other hand, in the case of the diffusion, the flow of carrier due to density gradient, it is called as density gradient, because there is a variation in the density. The higher, suppose it is E2 level and this is E1 level. So this energy level, the higher energy level, has more number of electrons as compared to the lower energy level. The density of atoms are in the lower energy level is lesser as compared to the E2. So there will be movement of electrons from E2 to E1. In the case of the photons also, it has been there. In the case of the laser, we have spontaneous emission and stimulated emission in the same way. So these are called as carrier transport. So we have defined these diffusion and drift current in terms of drift and diffusion current equations. So we have total current density, that is current per unit area. JP drift, that is current density due to drift of holes. JN drift, that is current density due to drift of electrons. Similarly, there are some terminology for diffusions, JP diffusion, JN diffusion, this is JN diffusion, and last one is the diffusion constant, and the mu is the mobility of the charge carriers. So we define diffusion current as a total current which comprises of both the drift and the diffusion. So it is four terms: JP drift, JN drift, JP diffusion and JN diffusion. And with the help of the Einstein relation, which is D by mu is equivalent to KT by Q, we define these equations in the later lectures. So KT by Q is equivalent to 26 millivolt. In the numerical problems, we can fix it at 300 Kelvin. We have K is 1.38 into 10 to the power minus 23, as we already know. And temperature, we fix it here 300 Kelvin. With this values, and Q is equivalent to 1.6 into 10 to the power minus 19. With this value, we can find out what is the value of the KT by Q, which comes out to be 26 millivolts. So these drift and the diffusion currents comprises of the total current density, and this will give you the overall flavor of the transport equation, carrier transport equation. So in the next lecture, what we are going to see, the carrier transport equations, how the conductivity and the resistivity will change according to the semiconductors, like if we are using N type or if we are using P type of extrinsic semiconductors, how these are changing. Thank you so much.